Okay, thank you very much. First of all, my colleague will start and I will take over doing the presentation.
Yeah. Good afternoon, everybody. Hello, my name is Philipp Schachinger, and together with my colleague Dennis Albert, we are investigating the effects of solar storms on power grids, and therefore we have to change the frequency which we are looking at a little bit, because in the last presentations we heard about kilohertz. Now we are changing into the direction of millihertz and DC. And there are these DC currents in our power grid, which have many sources, but one of the main sources are solar storms, which occur during solar eruptions on the sun, which are also called coronal mass ejections, which are actually clouds of charged particles which move from the sun towards Earth and cause a magnetic field variation in the Earth's magnetic field. And we all know the Maxwell's equations and the law of induction, and every changed magnetic field leads to an electrical field. And in our case, the Earth's magnetic field changes and therefore induces an electric field in the Earth's surface. So an electromotive force is flowing in our Earth's surface. And this electromotive force causes currents which enter our high voltage grids through grounded transformer neutral points and flow from transformer to transformer and causing many effects, which Dennis will later explain a little bit more. Exactly. So what we are doing as one part of our studies at Graz University of Technology is that we calculate those GSEs. We start on top with magnetic field measurements, do a little bit of transformation, and combine it with Earth models to calculate an electric field, which is a little bit simplified. However, it's good enough for our estimations. And with this electric field, together with power grid data, we calculate a driving voltage source. So it's basically a voltage difference between substations. And with the nodal analysis, which we all know from, for example, load flow calculations, we calculate those geomagnetically induced currents in every line and transformer and substation grounding, for example, in the Austrian power grid. And then we can correlate these calculations with our measurements. So we have 9 transformer neutral point measurements in the Austrian power grid, which are basically DC measurements. And with this data of the correlation, we can improve our grid models and our calculation techniques. And we do a risk analysis. Thank you. Which is then combined with transformer models. And we can estimate the impact of those GSEs on transformers and calculate, for example, reactive power consumption or harmonic distortion. Next slide, please. Thank you. We do it with our self-developed calculation tool. We call it low frequency current simulator, where we load magnetic field measurements, Earth models, and power grid data, and calculate those currents, for example, for Austria. And you can show it in many different ways. For example, as you see on the right picture, as circles which indicate the currents in transformer neutral points. If anyone is interested, you can download it for free from GitHub. You will find the link below. I think that's the basic of those DC currents which influence the power grid. And I'm handing over to Dennis, which will talk a little bit more about transformers. Thank you.
Thanks, Philip. Yeah, these DC currents or low frequency currents then entering our power grid, causing problems at the transformer. So as Philip already mentioned, we have the high half cycle saturation causing current and voltage harmonics. These harmonics then again causing the transformer to heat up if they last very long and are very strong. And accompanied by these heating and half cycle saturations, we also have a transformer sound. The transformer sound increases. So that small picture here on the right hand side of the slide just indicates the different frequencies, so the sound frequencies with and without DC. And here you see can really distinguish between a DC biased transformer and not. And that was originally the initial problem which initiate our project. So, but coming a little bit back more to frequency and impedance, to the actual topic of that conference. So the problem is if we saturate the transformer, we have first frequency dependency of the magnetic permeability of the transformer core, which reduces with increasing frequency. So I think these frequency here, 10 to the power 4, 10 to the power 6 is now the range where we talked about before. And the magnetic permeability is also dependent on the magnetic field H. So with increasing, I think most of people will know these characteristic, this pH characteristic, the magnetic permeability drops to basically the vacuum permeability. So, so if we causing transformer core saturation, we decreasing or driving the transformer into saturation, causing the magnetic permeability to drop, and this behavior is accompanied by increasing, let's say, harmonic content, and that also reduces the magnetic permeability. So we are changing the transformer impedance. Just to give you an example, this was a measurement from in our lab from a 50 kV or 250 kVA transformers, usually having a peak no load current of 2 amps, and we are here about we're having a back-to-back setup, so they were connected on the high voltage side, superimposed the DC via the high voltage neutral, and reached current peaks up to close to 100 amps here in the 1/2 cycle. In both transformers in no load, so there were no load or no power transferred by the transformer. It was just caused by transformer core saturation. And for example, this was a measurement just 1 or 2 weeks ago. We had an old transformer, 100 kVA, and we were allowed to do different tests with the transformer, also open the transformer here in the lab of the local power grid operator. And just to give you an impression how that frequency behavior of the transformer usually looks like and is measured, we have done this with a sweep frequency analysis. So different frequencies are applied at transformer, and then this curve are generated. So the red curve shows the transformer in no load conditions, so this, the low voltage terminals were left open, and the blue shows the characteristic with short circuit low voltage terminals, and below you see the phase shift. And it usually starts here at the first harmonic, or not the harmonic, the resonance frequency of the transformer, which is usually well below 1 kilohertz. And you can really distinguish between short circuit and no load terminals, or in no load condition. And yeah, that is basically what we do. And we're also interested in the topic of grid impedance, because we see a lot of, or at least we also have done measurements close to renewable generation units, so actually wind turbines, and we see a different behavior or different profile also in these transformer neutral currents than in other substations. So for us, it would also be interesting, and probably coming a little bit more into that topic of grid impedance with your measurement technique, your knowledge in that field, and connecting that with probably the power transformer data, our power transformer profile, and basically the GIC topic. So as the generation moves from, let's say, big thermal power plants towards renewable, small or smaller generation, this problem or this change in generation probably also affects our distribution stability and operability probably. So that was just a small little topic, something different about solar storms, power transformers and all that. And yeah, feel free to ask any questions. Thanks.
Yeah, thank you very much, Mr. Albert. Any questions here? Professor Kai and Dr. Do. Let's start again with Professor Kai.
Oh, thank you. But Dr. Do can also begin. Yeah.
It's okay.
Okay, thank you, Dr. Do. Yeah, thank you for the very good presentation. Thank you for both. And I have two questions. The first question, because I'm not quite familiar with this GIC induced current and voltage. How about the magnitude of such a current and voltage, and also how about the frequency? For example, the zero system frequency. How about this magnitude and frequency of this induced current?
Yeah. So if I may start, Dennis, if I'm missing something. The amplitudes differ a lot depending on the situation and location of the substation and the transformer. Okay. So in, let's say, geomagnetically quiet times, we have a load of 1 amp, for example, and in the last months, the level of GLCs rose a little bit. So we measured already 14 amps, but also depending on the storm and on the latitude where we are located, there can also be 100 amps or even more during serious storms, which then lead to serious effects on the transformer. Okay. To the frequency, those currents are very, very slow. So you can classify them into different, let's say, categories, but usually they are far below 1 hertz. Let's say 10 millihertz and slower.
Okay, thank you so much. Yeah, and another question is, I think at the presentation slide 7, I think. Oh, sorry, no, not slide 7. Measurement. Yeah, this one, yeah, slide 8. This is the measurement of the transformer, or is this some part of the grid?
Yeah, this is actually just the transformer depicted here on the left-hand side. That was before opening the transformer. We did the goal of this investigation or measurement were actually to measure transformer core phases, and this was the reference measurement before we start manipulating the windings and transformer core.
Okay, my question is that if it is a transformer, for example, the no load situation, the only impedance we have, or almost the most important impedance we have, is excitation impedance is quite high actually, and also it should be increased with the increase of the frequency. Why it decreased from around 1 kilohertz, and also it becomes also capacitive. From my experience, it should be inductive.
yeah, it's due to the winding capacitance, which comes into place with increasing frequency.
Oh, okay. Is that typical for such kind of transformer, or is I don't know why it is inductive, because the transformer, for example, the excitation part, it is a really, really large reactance. For example, for the no load situation, I don't know why it is capacitive. Do you have a filter somewhere there? Or?
No, it's just the transformer you see here depicted, and we have just connected the measurement device here on the high voltage and low voltage terminals for that measurement.
Okay.
And these are typical, let's say, curves for no load condition and short circuit condition of the low voltage side.
Okay. Okay, thank you. But I'm just curious about it. Thank you. Yeah.
Yeah, that's just showing how it looks like in let's say in our part of studies, and have it as as difference to the other curves we have shown before or seen before.
Thank you so much.
Welcome.
Dr. Do?
Yeah, maybe I have one additional comment to that. So I think it depends on the different models of the transformer, independency of the frequency. So at lower voltage level, you have inductive behavior, and at higher, the capacitive behavior, because if you consider the equivalent circuit of the transformer, so you have also capacitive, get to model that as also a capacitive of the windings and also to the tanks. And so you have inductive and capacitive. That's the reason, I would say. But my question is, if you look to the phase, can you explain why the phase is higher than 90 degree?
No, should be not higher. It looks like it's close to 90, but here it goes up at the resonance, at the point of resonance.
Yeah.
Or just right before the resonance point.
So it's a measurement for, I think, yeah.
Yeah, there's usually done a reference measurement, or really a 0 point measurement, and you need to correct these lines to that reference measurement. This is not done in this case here.
Okay.
Usually you can just subtract it in the software, and just subtract it, so you will be just below 90 degrees here.
Okay. Yeah. Thank you.
You're welcome.